Welcome, ladies and gentlemen. Good morning. May I have your attention, please? Thank you. At this time, go ahead and make sure that you've gotten a red mark for today, the 14th. Raise your hand if you did not get a red mark. Wonderful. Today we'll continue our discussion with functions, but we're going to add a new operation today. We're going to perform compositions with functions and function rules. We're going to both evaluate a composition of functions with a numerical input, a number value like we're used to evaluating functions. We're also going to perform composition of functions with variable inputs. Okay, we're going to compose a function rule within a function rule, and so we're kind of doing working from the inside out. We're going to do some multiple function evaluations today, and so I'm excited about that. But first, we want to make sure that you're comfortable, right, with your reverse and undo, your solving equation strategy as we get forward, get close to our Day 7 quiz day. For us, that's this Friday, right? You'll be having your first quiz that counts in Infinite Campus, and we want to make sure that that's a good one, okay? So let's go ahead and practice with our strategy. I made a little bit of room here. Recall that we've got multiple operations going on, and we can develop a recipe for success if we reverse and undo our forward steps. And so we think back to middle school, cover up the equal sign, and pretend we were just evaluating that expression on the left. If I were to substitute in a variable value for x, everywhere I see it and work it out, the first thing I do to evaluate that would be to plug in x in, add 6 to it. So my first forward step would be plus 6, and then we take the square root. Then we multiply by 2, and lastly, add 3. So we'll have our forward steps like that. Now we'll go ahead and replace that with 17. We'll reverse and undo these forward steps as a means for developing my recipe for my solving steps. And so let's go ahead and see what that'll look like. If my last forward step was adding 3, my first reverse and undo will be subtract 3. Then we'll undo multiplication by 2 by dividing by 2. Then we'll undo square root by squaring. And so my shorthand notation will be raised to the second power, but that's just squaring. And then lastly, undoing an addition of 6 would be a subtraction of 6. Let's go ahead and apply those solving steps now. Okay. So our first thing was subtract 3 from both sides. So subtract 3 from both sides. Awesome. Now we're ready for our second solving step. Divide both sides by 2. That gets our radical alone, and we're close. Now we just have to square both sides. So we'll go ahead and show that by writing a parentheses raised to the second power, right? Squaring both sides. That undoes the radical and gets my x plus 6, the quantity inside the radical, out of the radical, out of the parentheses. It's on the ground floor now, ready to go. On the right-hand side, 7 squared is 49, and we can now finish it out with a subtraction by 6. So subtract by 6. Go gadget arm. And I'm left with x equals 43. Before I box that, I want to do a quick check. So I'm going to take that potential solution value for x, go into the original, and I'll even follow my green forward steps and make sure it makes a true statement. If it does, I'm confident it's a solution to my original equation. So here we go. 43 in for x, plus 6, 49. Square root of 49, 7. 7 times the 2 in front, 14. 14 plus the 3 is 17. It makes a true statement. Woohoo! So I'm confident that this is correct. And I'll go ahead and box that now. All right, I'm dying to know, did anybody else generate 43 as a solution before I did? So who else had 43 already? That's great. Thanks, hands down. If you didn't, go ahead and write down, right? Go ahead and write down these forward and solving steps. That's going to be your key to success on the upcoming quiz. Can you reverse and undo those forward steps so you have a strategy even when there's multiple operations in the same problem? Awesome. Let's go ahead and take a look at our evaluation. So I know that we can evaluate function rules. If I'm given an algebraic function rule, that is an equation, I can evaluate that function simply by rewriting its function rule. Except everywhere I accept inputs, I'm not going to put that x variable input. Everywhere I see an X, I'm not going to put X. What am I going to put, Will? 4. Excellent. Thank you. So here, let's do it. I'll go ahead and do the order of operations dictate the squaring occurs first. So I still have the 2 times out front. We'll do the 4 squared with the exponents first. That's 16. And then minus 5 shown on the back side. 2 times 16, now multiplication comes first. And finally, 32 minus 5, I get to the 27. Raise your hand if you already had 27. 27. Great work. Thank you. Hands down. And we can use mapping notation as well. If I have a function named g that accepts input values and maps them onto outputs in accordance with the rule of 3 times my input x, then I can evaluate a function with a variable input as well. I'll simply go to my function rule everywhere it accepts inputs, and instead of putting x, instead of putting 4, I'll put quantity w minus 2. So I'll go ahead and go to my 3 times input. Inside my input, we'll put w minus 2. And we'll use our distributive property to simplify. So we're in a fully simplified form. And I get 3w minus 6. Raise your hand if you already had 3w minus 6. Did anybody get to the end with the variable? Great work. So you can finish it out by distributing through. And we expect you to simplify within reason, right? On your quiz, we'd expect you to be able to write your answer in fully simplified form. What questions do you have on today's bell? Great work. Then let's go ahead and take care of our housekeeping. If you could kindly take out your assignment number 4 now. Assignment number 4. Make sure that you have your name first and last. 1A and number 4 clearly labeled on your heading on the top right of your assignment. Give yourself credit for those that you completed from the bookmark out of 32, please, in pencil. Divide, enter, multiply by 4, and a single reading question today. If you showed me your 8-1, you guys have been doing a good job completing your reading questions. You're eligible for that 5th point. Then round your final answer and box that nice and big. Round it to the nearest half point in pencil. 0 to 5 for your Infinite Campus score. And what questions do you have on your Infinite Campus score today? Okay, then let's go ahead and do pencils down, please. Pencils down, and we'll switch over to our grading pens. Nobody should have their pencil anymore. We're not getting down any answers. We're just checking them for accuracy. And with your grading pen, let's go ahead and check our answers now. Recall that we can use our graphing calculators now with tracing. After we've entered a function in the y== menu and gotten a suitable window for viewing, we can press trace and the cursor will jump on the function and we can scoot along that function using the right or left arrow keys, just like we did last class. Remember, you can use a mod symbol or a colon when working with interval notation. The textbook favors the mod symbol and I favor the colon. Number 9 is an integer, rational number, and real number. 10 is rational and real. 11 irrational and real. And those are some examples of rational numbers, integer, irrational number. You could make up your own for 12, 13, or 14. And hopefully after our discussion in class, you had lots of examples. Continuing on. The set of all y's, such that y is in between 0 and 24, inclusive. 15b after 17 years. And C, D is in between 7 and 12, inclusive. 17a is 5. B, x can be anything, right? X can be any real number. And y, set of all y, such that y equals 5. And 18, a is -7, any real number, and then that parabola, that upside down U shape, only produced y values that were less than or equal to -7. It was an upside down U shape, and we're going to look more at that in the upcoming week. 19a is 4, bx is 7, 21, there's a picture. B, 5.64 feet. And 22B is negative 11. 25, R is 261. That gives us 60. 26, X equals 8. And that gives us 3 halves times 8 would be 12 plus 4 is 16. And 16 does equal 16. One page to go. Zero miles for 1. 2 after 75 is about 9. After 75 minutes, Frank was about 9 miles from home. Number 3 is 12. Number 4, you can list domain values if this is from a table. 0, 4, 9, 16, 81. The range, negative 3, negative 2, 0, 4, 9. 5A is 4. B is negative 2. 6 is 81. 7A is 5.19 inches. B after about 5.6 days. 8, no. You could always break it into smaller units of time, so you can continue finding smaller and smaller increments of time. 10, 2. P is 2 kilometers ahead of Maria after half an hour. B, T is 1. Maria and P are the same distance in the race at this time. And C, no. Maria completes the race in 1 3/4 hours, but Pia takes 2 hours to complete it. 11, yes. With domain negative 3, negative 2, negative 1. 0, 1, 2, 3 in the range, those corresponding outputs. 12, no, not a function. There's more than one value for y assigned to certain values of x, so it's not a function. 13, yes. With listed domain values. 22a is 4 pi r squared, and b is the dependent variable. R is the independent variable. As you're finishing up, go ahead and give yourself an accuracy fraction about out of how many you did. About how many did you get right? Please a final check that your heading is correct, name first and last, 1A and number 4 clearly labeled on top. Make sure your infinite canvas score is boxed nice and big in pencil, round to the nearest half point. If you'd staple multiple pages together, that'd be awesome. There's a stapler on the side table there. There's also a stapler on the front table. And then go ahead and pass it from the back to the front, please. Front rowers, if you make sure they're facing the same direction, I'd really appreciate that. Keep them in the same column, please. Thank you. Thank you. Very good. Thank you. I appreciate your help grading your assignment each and every day, ladies and gentlemen. All right. Today we're going to find values and rules for composite functions. Composite functions just means that we're going to involve more than one function evaluation in the same problem. So instead of like number 2 and number 3 in your bell work, where we plugged in a value or a variable into the input and simplified, we're going to be doing 2 or more steps when we perform our composition. We'll still be plugging in inputs, it's just that we'll have to find an intermediate step, an intermediate value that will then be plugged into another function before I can get my final result. And so basically, it's function evaluations with subsequent evaluations. We have to do more than one evaluation when we find a value for composite functions. We're going to solve real-world problems that can be modeled by composite functions as well. So what I want you to do is go ahead and think back to geometry, right? So while it may bring shudders for some of you, and it might be one of your more light classes for others, let's think back to this notation. So what did we do if we were going to perform this particular transformation? And so what I want you to do is raise your hand if you remember what the R stands for. What does the R stand for in geometry? Don't call out. What does that R stand for in geometry? Thing stands down. Adam? Reflection, right? Reflection. And this little circle here is a composition symbol, right? A composition symbol. So here it looks like we're going to perform a reflection with this given triangle, ABC, and we're going to work from the inside out. So my first transformation would be a reflection about the line N. So I'll get a new image. We're going to reflect over line N. So here we go. Oh, it's already reflected over line N. And then we're going to reflect over the new triangle over line M. And so see, we went from the inside out. There was our first reflection, got this middle image, and then we worked from the inside out and then went over line M last, and so we ended up down there. A function composition is going to be the same deal, where we perform more than one function evaluation subsequently. Let's go ahead and take a look at our function rules here. So the composite of two functions is a sequence of a rule following another rule. Think of the rules as function machines. And so here we have our function machine F. It's a pretty sweet little graphic. Then we've got our function machine S. And we're going to go ahead and perform a composition, just like in geometry when we did the reflection, right? Followed by a reflection. Here we're going to do a function evaluation, followed by another function evaluation. You're going to work from the inside out. So my first evaluation will go into function F. Here we go. Let's take that inner value, the 7, the input, we're going to plug it into my first function, the innermost function, F. In accordance with some rule, it'll work it out. So I went ahead and put in 7 into F. So I got 49 minus 64, and that equals the negative 15. That's my intermediate value. I'll now take that and plug it into my outermost function. My second function, my S function, that accepts inputs and pairs them with outputs in accordance with the rule 1 over input squared. So I'll put negative 15 there. And I'll get 1 over negative 15 quantity squared, and that equals 1 over 225. And so a composition of functions, you work from the inside out and you perform 2 or more function evaluations where order matters. Work from the inside out just like with your reflections. I know you guys are going to rock style this to the top. And now, the moment you've all been waiting for. No, not that rule, not that moment, Logan. It's super duper page animation time. That's what I'm talking about. So super duper page animation time. We're going to be able to watch this in full effect. And I want you guys to focus on the order. So let's consider 2 function rules, F and S, as in the previous graphic. But now let's start with an input value of x equals 2, and we'll go ahead and put that in my innermost function F. Let's see if we can watch the order. Ready? So there goes 2 into my inside function first. In accordance to its rule, 2 times input plus 3, that produces an intermediate value, 7. That comes out of my first function, and now I'll go ahead and input that into my outermost function where it accepts inputs. Input minus 4. So there's my 7 minus 4 equals 3. And 3 will do the happy dance because function evaluation is fun, especially in 2 steps. But 1 time's not. What's better than 1 time? 2 times. 2 times. So here we are in innermost function. Work from the inside out. There's F's rule. That produces an intermediate value. Plug that into my outermost function everywhere it accepts inputs. Input minus 4. That's 7 minus 4. And I love the number basket. Here comes my answer. Celebrity. You celebrate. That's fun. Oh gosh. I love math. Let's go ahead and do some practice now. And we'll work from the inside out. And so we can write with composition symbols, or we can use parentheses. With parentheses, it's easy to see what the innermost function is. And so let's go ahead and evaluate f of g of negative 3. So f of g of negative 3, we'll go ahead and work from the inside out. So I'll do f of, and let's go ahead and I'll do g of negative 3 in green. So I'll go to G's rule, and I'm going to go ahead and go to G's rule 2 times input squared. And in G's rule, I'm going to plug in the x value, negative 3. So look, we're working from the inside out. I still have f of g of negative 3. But G's rule in green, 2 input squared, I'm going to evaluate using the innermost value, the x value, negative 3. Let's do it. So I have f of, and now I can go ahead and evaluate inside. I have negative 3 squared is 9. So it looks like g of negative 3 is 18. Now I still have my outermost function. My outer function is f in blue. So I'll go to f's rule. F's rule accepts inputs and then adds 5 onto them. So my last part would be taking that inside value, that g of negative 3, and adding 5 onto it. It looks like my final answer is 23. So it's a 2-step evaluation. First, negative 3 goes into G. Follow its rule. Negative 3 squared is positive 9 times 2 is 18. There's my intermediate value. Now plug that into my outermost function, f. Everywhere it accepts inputs. 18 in for x, 18 plus 5, 23, final answer. Does order matter? Let's see. Let's perform the function evaluation g of f of negative 3. G of f of negative 3. So I'll go to g of, and now I'll go into f's rule for my innermost function, input plus 5, and I'll go ahead and plug in my x value, negative 3. So once again, I'm taking the same x value, negative 3, and I'm plugging into my innermost function. It's just that this time my innermost function is f. So I go to f's rule. So in f's rule, I plug in negative 3. Negative 3 plus 5 is 2. And so my intermediate value is 2, and I'm going to plug that into my outermost functions rule. That's g. G is 2 times input squared. And so I'll rewrite that as 2 times input squared, except my input is 2. And we'll go ahead and work from the inside out. It looks like exponents come first. But this time I get 4, and then times the 2 last. Final answer, I'm getting 8. Let's go ahead and do a quick recap. I took negative 3 for my x value. I plugged it into f first. Negative 3 plus 5 is 2. I took that intermediate value 2 and plugged it into my outermost function second. My outermost function took 2 and squared it, got 4, and multiplied by the 2 in front to get 8. What questions do you have about our function composition with the value for my input, with the value? Not only can we perform function composition with x values like negative 3 or 7, we can also perform function composition with rules. And so in this case, we're going to take my innermost function, in this case g of x, and I'm going to plug it into my outer function f. If I have variable inputs in my composition, I'm going to have variable outputs. I'm going to have a new function rule that has x's in it. So once again, if I plugged in a number for my function composition, I'll get a number at the end. If I plug in a function for my input, I'm going to get a function at the end. So I'll have x's in it if I'm plugging in x's. Let's go ahead and find an expression for f of g of x and an expression for g of f of x. So I'll go ahead and do g of x in green. And I'll do f of x in blue again. So I'll go and do f of g of x. That says go to f's rule. And f's rule is 3 times input plus 5. Except everywhere you see an input, this x right here, I'm going to put the entire green function, g of x, which is 2 over x. And so I'm going to show that, and hopefully the color coding will help some. I went to f's rule. Everybody see f's rule? 3 times input plus 5. But I put g's definition into f wherever f accepts inputs. So I get 3 times 2 over x plus 5. Now I'm ready to simplify. So it looks like I can just do a fraction. So I slap that 3 over 1 and go straight across. 3 times 2 is 6 over 1 times x is x. So my final answer is just a new function. F of g of x is 6 over x plus 5. We took my innermost function, we stuffed it into my outermost function where it accepts inputs. I guess you could say that's pretty sweet. Does order matter? Well, it certainly did for my function evaluations with the value, with the numerical value input. I wonder if it matters for an algebraic input. Let's go ahead and do the same thing. G of f of x says go to G's rule. G's rule is in green, 2 over input. So I'll write G's rule, 2 over input, except everywhere G accepts inputs, right there, that x, I'll replace it with F's rule in its entirety. What's F's rule? F's rule is quantity 3x plus 5. So I put F's rule, right, into G's definition everywhere G accepted inputs. There's the x. I replaced the x with the whole function f in blue, 3x plus 5. Does everybody see G? G's function? There's the input. All right. I may or may not be able to simplify. In this case, this is as simplified as it gets. So I'll go ahead and write it one more time without the parentheses so it looks nice. This is be simply 2 over 3x plus 5. And that would be my final fully simplified answer. Did I get the same function when I did g of f of x as when I did f of g of x? No. So does order matter when I'm performing a composition? Right? Does order matter? Brady?
Yes.
Yeah, absolutely. Right. Order matters when I perform a composition with functions. Awesome. All right, let's go ahead and consider the domain of a composition of functions. And so once again, I can find a new function rule by performing my composition. I'll take my innermost function and cram it into my outermost function's rule everywhere it accepts inputs. But for this, we're going to add a twist, and we're going to consider the domain of my intermediate functions as well as my final function. So let's let x be a real number. We'll let t of x be 1 over x. And g will be given by g of x is x squared minus 100. What's the domain of the composition t of g? T of g of x. Well, what numbers from the number basket that we saw in our earlier page animation will we be able to use? So let's go ahead and think about this in a two-step process. Letter A, what values are not allowable for x in the function t of x? So everybody will go ahead and focus in on t of x. And remember, our domain asks us what values are we allowed to plug into my function. And sometimes it's easier to consider what values of x are not allowed to be plugged into my function rule. So what do we think are problem values for t of x? What do we think might be some problem values for t of x? Margot?
0.
0, the x value? How come? Good. We can't have a 0 on the bottom of a fraction. So if my function definition involves fractions, then I cannot allow x values such that when substituted in, create a 0 on the bottom of a fraction. And if I plugged in 0 for x in my t rule, then it would produce a 0 on the bottom, so that's not allowed. Good. So let's state the domain of t of x. The domain of t of x is the set of all x values such that I had no problem with positive values of x, no problem with negative values of x. I just couldn't let x equal 0. So to say that, we'll say the set of all x such that x doesn't equal 0. That's the quickest way to say that. Everything else is just fine. We just can't let x equal 0. Now let's state the domain of g of x. All right, as I look at g's definition, it takes inputs and squares them and then subtracts 100. As you think about your function rule, are there any values of x that it's not okay to square? Can I square positives? Square negatives? Can I square 0? Yes, and so because there's no fractions in g's rule, and there's no radicals, right? I can't have a negative inside a radical is my other domain concern. All values of x are just fine. So all real x's All real x's would be my domain for g of x. All right. Now it gets interesting. Now let's consider the composition of functions. So what inputs for g of x will produce values that are not in the domain of t of x? What? What inputs for g of x will produce values that are not in the domain of t of x? Well, t of x couldn't have a 0 on the bottom. As I look at g of x, are there any values of g of x that would make problems for t of x if I plug them in? Mark? 10? Why do you say 10? Got you. So g of 10 equals 0. And if I plug 0 then into t, it would make a 0 in the bottom fraction. Excellent. Are there any other values that I need to be concerned with? So I had 10. Margot? Negative 10? So negative 10 also causes problems for the same reason Mark discussed. When I take negative 10 and square it, I produce positive 100. Minus 100 is 0. Again, and it's not okay to plug 0. So we've got two problem issues. Everything else is okay. So I can now state the domain of t of g of x. So the domain of t of g of x, right, is the set of all x values such that x does not equal 10 or negative 10. How can we write that? So we could go ahead and write that as the set of all x such that x does not equal, and we could just do plus or minus 10. Would be a nice succinct way to write that. The reader now knows that everything else for x is okay, except x cannot equal positive or negative 10. Awesome work. All right. For your partner, I'd like you to go ahead and do the same thing now for a new composition. That is S of x. S of x. I want you to talk quietly with your partner and come up with the response. I'm going to walk around the room, and if you have a question, please catch my eye so that I can swing by and I can yell at you and your partner. Talk with you and your partner, right, as I'm walking around the room. Thank you. Let's find the domain and be ready to share.
For the S of x one, x is 0. X for f of x can't equal 8 can't be. It's not equal. Can't be 8 or negative. What else equals 64? Okay, you got it right. Oh, it can't be. Wait, no. You have the right thing.
Okay, ladies and gentlemen, may I have your attention, please? Thank you. I heard some great conversation as I was walking around. Before we get to the final answer for my domain, S of f of x, I would ask that you share what the inner function is and what the outer function is based on the location of this composition symbol. So if I were to write this with parentheses, what would be my inner function and what would be my outer function? Right? What would be my inner function and what would be my outer function? So how could we put that? Aaron?
The inner function would be f of x.
Okay. And the outer function? So if we were to rewrite this, thank you, I could write S of f of x. Then we can explicitly see the inner function there is my f of x. So my f of x is my inner function, thank you, Aaron, and my s of x is my outer function. So we're concerned about if there's any outputs of this f of x function that would make, right, that would cause problems for inputs in that s of x function, because we work from the inside out. So what did you guys find for your final domain then, based on that composition order? Heather? Positive and negative 8 were the domain, or couldn't be the domain, right? Yeah, couldn't be, absolutely. So positive and negative 8 are my problem x values. Raise your hand if you had x cannot be positive or negative 8. X cannot be positive or negative 8. Excellent work, that's exactly right. Thank you. And so we know that S of f of x is the composition, right, is the composition and we saw that if x is 8 or negative 8, squared equals 64, minus 64 equals a 0 on the bottom. And the squaring on the bottom isn't going to fix the 0. Right? 0 on the bottom squared is still 0, and that's bad news. And so my final answer would be the set of all x's such that x cannot equal positive or negative 8. And you guys did a great job with that. Okay, let's go ahead and consider a variable input now, f of g of x. And again, this is your opportunity to show me that you get it. So I want you to go ahead and perform this composition. It is okay to check with your partner, but you have to show me now that you get the order and the composition on your own. We'll come back and check it together, but I want to walk around the room. And if you have questions, make sure that you're catching my eye. Make sure that you have the order of your composition correct. And you can check with your partner too. Make sure that you guys agree. And I'm going to have you guys share on the whiteboard. Go what the inner function is, and go what the outer function is. X roll right there with X. So you're going to start out with 2 big parentheses, close parentheses, plus 3. And then right there where the big parentheses are, where the X was, you're going to put all of these. Yeah. Good. You're welcome. And you don't have to do domain placement. So guys, this is not a domain range question. This is not a domain or range question. It's just the composition. With a variable input, right, with a function input, you should get a function output. You'll get x's. There's no things I would say. Casey, how's it going?
Oh.
That's exactly right. That's right so far. You're not. You have an X rule. F is 2 times input plus 3. Rewrite that. Nope. Next line. That's right. We got it. What do you want? No more F. Now you're going to put 2 times big parentheses. Nope. Half of the 2. You're rewriting this rule. So 2 parentheses, space, 3x. Don't put anything inside parentheses. I want you to rewrite this instead of x like yes. What are you going to put in there? You're going to put in G's definition. 1.5 x minus 1.5. You're going to put that in where that little x was. Where that input. Okay, ladies and gentlemen. I saw some good things, right? I saw some good things and I saw some confusion. Let's come together and make sure that we're all comfortable performing a function composition. So let's go ahead and take a look. F of g of x says go to my function f. My function f that accepts inputs, 2 times input plus 3, and rewrite it. There's f's, my outer function. There's my outer function f's rule. Except everywhere f accepts inputs, don't put x. What am I going to put? I'm going to put g's definition in its entirety. G's definition was 1/2 x minus 1.5. And so I'm going to put 1/2 x minus 1.5 into f's rule everywhere it accepts inputs. Perhaps this will be better if I do an intermediate step. And so my first step would be f of, and we'll put my green function rule. G of x is 1/2 x minus 1.5. I saw this on a lot of people's paper. This is correct. Then I went to the blue function rule, 2 times input plus 3, and I put G's rule in for my input. And now we'll go ahead and simplify. And so we've started the ball rolling now, but we need to simplify. So we'll go ahead and distribute my outside factor through the parentheses, term by term, in accordance with the distributive property. 2 times 1/2 x is 1x. Minus 2 times 1.5 would be 3. Then plus 3 chilling on the backside. Now I can combine like terms. Same side, same operation. Negative 3 plus 3 sums to 0. And 1x, right, can be rewritten simply as x. It's bad math manners to write a coefficient, right? A coefficient of 1. We don't need that. We don't need that. And so I'm just getting x. Raise your hand if you got that. Anybody else get x? You did? Way to go. That's awesome. Good work. And so you can do working from the inside out, and you're going to have lots of chance to practice. Margo.
Oh, I was just reading.
Oh,
sorry, I
good.
just got distracted.
No problem. Way to go. All right, so we're going to close out our discussion today with the big ideas for closure, and then you're going to have some work time where you can earn up to 4 stamps today, up to 4 stamps as we practice the composition while you're in class. These stamps are like red marks, and then we count them up, and you get credit, right? Like you're solving equations, activity packet. We count them up before your unit test on a review day, and you get credit in Infinite Campus just for completing your daily work and your classwork, and that's going to be a great opportunity for you to practice the composition because it can be tricky. All right, but first, let's go ahead and perform our closure. So when evaluating the composition f of g of -7, what evaluation is performed first? Don't say out loud. Go ahead and write down. And when determining the domain of a function given by an equation, what must you be concerned with? And so far, we're concerned about 2 different things when we're talking about operations with real numbers. And I'll be asking you to share with the whole class. So what do we do first for that composition? And then what are we concerned when we talk about domain? Okay, please tell the class what evaluation is performed first when I perform the composition f of g of -7. So what is it that you're going to do first? Ben?
G of -7.
Raise your hand if you had plug in -7 to g first. G of -7. That's the inside evaluation. That's the first step of evaluation. Good job. So my first evaluation would be plug -7 into g, my innermost function. That would be my first step. Way to go. When determining the domain of a function given by an equation, what must you be concerned with? Right? And I saw lots of people talking about what domain is. And so what are we referring to when we're talking about domain? Taylor?
It says you're concerned with the values that would not work plugged into.
Absolutely. We're concerned with the x values that would not work, would not be allowable based on my function rule. That's absolutely right. What I want to know is what those concerns are, right? So we're concerned about x breaking some math rules. What are some math rules that we're concerned about right now? So we ran into a couple. Olivia? Yeah, fractions, right? Fractions, and what about fractions specifically? And what about fractions specifically? Dividing by 0. So we can't have the 0 on the bottom of the fraction, right? So we'll go ahead and put that. We can't have a 0 in the denominator of a fraction. And one more that we've had in passing, but we haven't spent much time on, Margot?
You can't have a negative number like inside of the square root.
Absolutely. So we're concerned about any x value such that when substituted in would create a negative inside of a square root. All right? So we can't have a negative number inside of a square root. And it turns out we can't have a negative inside of an even root when we're talking about the domain for real numbers. We can't have it inside any even root, but for now we'll just say square root because we haven't dealt with any other roots like fourth roots or sixth roots or eighth roots. Inside a square root will be good for today's closure. Awesome. What questions do you guys have about our discussion? In just a minute, you're going to have an opportunity to practice and earn stamps, and earn blue activity stamps while you're in class, okay? There's two different worksheets. Everybody find building functions, please. Building functions. At the end of the first page, number 5, and the end of the second page, number 10. After you complete all exercises, you're going to check them with the posted answer keys. Everybody look at the back whiteboard. There's building functions on the left and rewriting formulas on the right. On the side whiteboard, if you're closer to this side of the room, you're welcome to consult these answer keys where I've shown my work and boxed my answers. Building functions on top, rewriting formulas on bottom. The answer keys are there, right, for you to use, but they're there to be used appropriately. So what you're doing is you're working through, and you're checking your answers to make sure you're doing it correctly. You don't want to get all the way to the bottom and realize you've done it wrong. You want to check each time. You're just not standing here and copying down the answers. That doesn't do you any good. So once again, the answer keys are meant to be used, but they must be used appropriately. So please, after you've worked through the first side and checked all your answers, you're going to come up to the front desk, and I'm going to issue a stamp for number 5. After you've worked through the back side and checked all your answers, you're going to come up and get your stamp for number 10. Then you're going to switch gears to your rewriting formulas worksheet. Again, I've shown my work. I've listed forward steps and reverse and undo solving steps. You're going to work through an order and check your answers when you are done with the side 1. Then you're going to come up to the front desk and you're going to get number 4 stamped, and then again the same process for the last number 7. You've got a nice chunk of time, and if you work diligently, you should get all your stamps and have a chance to begin working on your number 4 assignment. What questions do you guys have about what the rest of the day is going to look like? You may work with your partner, that's fine. We're not going to scoot into our regular cooperative learning groups, so we're not going to be moving the desks around to form our cooperative learning groups. Instead, we're just going to practice. It is okay to talk with your partner, that's fine. Make sure you're checking your answers. Great job today. And I'll go ahead and stop the recording now. Thanks for getting started right away. Good job.